Image convolution is probably the most important operation in image processing. I'll start the talk about convolution from image noise. There are several types of image noise, but I will consider only one of them, additive Gaussian noise. In this case, noise is added to the true signal. Intensity of the noise is drawn from a Gaussian normal distribution. Each pixel is corrupted randomly and independently from all other pixels. Given a camera in a static scene, what is the easiest way to remove the noise? Because noise is random and independent, the simplest way is to capture several images and average them. Because noise is random, averaging will reduce it. But usually we have only one noisy image and cannot average several images, so we need to devise another way for reducing the noise in image. Instead of averaging pixels in several images, we can replace each pixel x with weighted average of his local neighborhood. Weights are jointly named a filter kernel. The simplest case is equal weights. This particular filter is called the box filter. Sum of all weights in a filter kernel should equal to 1, so that applying the filter does not change overall brightness of image. For clarity, we can write the common factor separately. The process of filtering the image with weighted averaging is called convolution. Let f be the image and j be the kernel. The output of convolving f with j is denoted f star j. Each pixel with coordinates mn in the result of convolution can be computed as sum over all k and l of products of f sub m minus k n minus l by j sub k j. We can visualize convolution as a scanning of image f with filter kernel j from top to bottom. The simplest filter is identity filter, where only one weight in the center of filter kernel equals to 1 and all other weights equals to 0. Applying this filter kernel for image convolution will result in no change in filtered images. But if we move the only one from center of the kernel to the other place, then the image after convolution will change. It will be shifted. In this case, it will be shifted left by 1 pixel. Generally, any filter kernel with all positive weights and with sum equal to 1 will be image smoothing filter. Here is the example of box filtering image with a lot of fine details. You can see that a lot of spurious lines in the right image appear after smoothing. We believe that smoothing operation should look like an image from a defocused lens, because it introduced blur to the image, and we can see that smoothing with average doesn't compare at all well with defocused lens. If we try to apply averaging to a single point of light, we will get a little square. If we see the same point light with a defocused lens, it will look like a fuzzy blob. We want to devise a filter kernel that will produce the same effect as defocused lens when applying to the point of light. To reach these results, to eliminate edge effects, weight contribution of neighborhood pixels should be according to their closeness to the center, like this image of fuzzy blob. We can set filter weights according to two-dimensional Gaussian distribution, centered at the filter center with arbitrary sigma. In this particular example, sigma is set to 1, and filter size is set 5 by 5. Filters with weights distributed according to Gaussian distribution are called Gaussian filters, and they are probably the most used filters in image processing and image recognition. Gaussian filters have infinite support, but discrete filters use finite kernels. For the same sigma, we can build filters of different sizes. Here, for the sigma equals 5, two filters with sizes 10 by 10 and 30 by 30 are given. Notice that for the second filter, the weight near the boundaries of the filter are close to 0. As a general rule of thumb, we usually set Gaussian filter half-width to about 3 sigma. So the total size of Gaussian filter equals to 6 sigma. In this case, as demonstrated in the slide, all weights near the edges of the filter are close to 0. Here is the comparison of smoothing with box filter and with Gaussian filter. Please note that spurious lines in the left image are absent on the right image. It can even be proved that Gaussian filter is the only filter that doesn't add any additional information to the image, so no additional signals or spurious lines can appear when applying Gaussian filter. This is one of the reasons why Gaussian filter are so extensively used in algorithms. Applying Gaussian filter can reduce noise in image, but it also blurs the image. The larger the intensity of noise, the larger filter kernel should be used to remove the noise. But the larger the filter, the stronger is the blur. So it's a compromise between smoothing of the image and reducing the additive noise. Image convolution can be used for many tasks. For example, we can use image convolution to reduce image blur and make edges more pronounced. The idea of this process is very simple. Let's try to apply blurring and subtract blurred image from original image. What does blurring take away? It is information regarding sharp edges in images. We can add this information to the original image with some scale factor, and this will make edges more pronounced, more sharp. So this operation is called image sharpening. We can combine all operations into single convolution and approximate with negative Laplacian of Gaussian. Such filter is called unsharp mask. On this slide, you can see an example of image sharpening with this specific kernel. You can see that edges in the image are more pronounced and the image looks sharper. The left image in the slide looks a bit blurrier than the image of the right. Sharpening produces visual pleasing results usually, so it's often used in consumer cameras to improve the quality of images. And you can only turn it off if you try to capture the raw images with no post-processing.